All right, no wait, not afternoon yet. Good almost noon, everyone. My name is Jimmy Bogard. That picture in the front out there was not me. I don't know who that is, but yes, that was not me. This is me. We'll see. So I'm only going to say this once because I keep screwing it up, but today we're going to talk about modularizing the monolith. I got it, yes. You can find me on Twitter at @jbogard, or X, whatever we're calling it these days. And this presentation will be my GitHub later, as soon as I remember to upload it. And I blog about this topic sometimes and others on my blog at jimmybogard.com. So yeah, how did we get here? In the situation where there's been this like big pendulum swing where monoliths were bad, everyone should get rid of them. Then we went all the way over to microservices, and then now we're like trying to pull the pendulum back again. And so a lot of this talk is my experiences both building systems using microservices, as well as taking existing apps and then breaking them down to smaller components, smaller modules, and the process we use to get there. But we didn't want to be in this negative place. It started out good. And we started with a single application. We pushed it to production. We started adding more and more features. That kept working. But we noticed that over time, it became harder and harder to add features to our system. That every time we tried to make a change, we spent the majority of our time not actually doing the important work, which is coding. We were doing most of our work making sure that we didn't break anything else in the application. And so over time, it just became worse and worse until we got into this, either a big ball of mud here or there, or perhaps both. And now it's just this really big tangled mess that is really difficult for us to figure out what the heck's going on and to be able to change it. So we started looking at other alternate architectures to see are there ways for us to break the system apart into smaller pieces to make it easier to change. And so we might even break things up into like the front end and the back end. And so I've seen this a lot as well, where we do, like, instead of having just a single server-side application, we now break it into the front-end application and then the back-end application that has APIs and stuff. But still, even breaking up into these components, we still ran into the problem of eventually a big ball of mud. So the solution, of course, was to take this and break it up into smaller pieces, into smaller services. And that was the promise, right? That if you could break this big system up into a smaller set of services, then allegedly you should be able to build the systems more quickly and more efficiently, can scale more easily, all those sorts of hopefully good things that we've been sold on services and microservices, that sort of thing. Now, I have done many talks on microservices, so I guess I'm one of the people to blame for us getting into this mess of microservices that are bad now. But I think the thing that I saw was not that we were building like this picture, where it was just a single application with 5 or 6 services. Instead, it was more like 1,000. We had really, really exploded out the number of services to the point where it became difficult to understand if I need to make a change, how all those pieces fit together. So I think the main problem here is that in the microservices area, the term micro was way overemphasized, and the term service was just misunderstood. And so putting those two things together is how we got into this really big mess of thousands of microservices, and we don't know how anything fits together. The other big challenge I saw was when I see folks undergoing this journey from taking an existing system and breaking up into smaller ones. Microservices are not the easiest thing in the world to develop with, right? We're now building distributed systems, and distributed systems are hard. And one of the other really hard things about building these kinds of systems is defining those boundaries. What should each boundary of each service define? What capability should belong inside of it? And because it's often pulling in new technologies and all sorts of new ways of developing, oftentimes I see these kinds of efforts undertaken as sort of like a glorified rewrite of an existing system. And rewrites almost always fail as well. So I guess it's not no surprise that these big re-architecting efforts of going from a monolith to microservices are often ending in disaster because it's just so hard. One, it's so hard to build distributed systems. But two, it's often built as like, okay, we're building the second system off to the side that is the microservice panacea, but the existing monolith has to keep getting features added to it over time. And one of the things that's really challenging about these services is you don't know if your boundaries are correct until pretty late in the development process. I've seen cases where teams were independently building services and everything worked great, and then when we tried to go to production or even a test environment, the application completely crashed and burned and didn't even work at all. And we asked ourselves, well, how do we get into this mess of we were able to build these services and develop them locally just fine, but they didn't work at all when we went to any kind of deployed environment. And it was because locally we're not in a distributed environment, right? Everything is local host, nothing is going over the network, and so it's very easy for us to build services that are high performance when they don't have to actually, cross the wire to talk to anything else. But it's hard for us to know that that's going to happen until we actually put it into a distributed environment. And if we're wrong, then that could mean months or even years of wasted effort between all the different teams. So the boundaries are the thing that's really hard for us to get right. Distributed systems are even harder to deal with, and doing both is harder. Like if you try to do get the boundaries right, and you're trying to also do distributed systems potentially for the first time, then combining those two things together is a very, very challenging, very challenging effort. So, then we don't do that anymore, right? Let's throw out the microservices idea and just go back to the single application and just a single monolithic system. But we want to avoid this big ball of mud. So how do we continue down this monolith concept, but avoid all the bad things that you typically think of in terms of monoliths? So first, what can we define a monolith as? I've had a lot of definitions over the years, but this is probably the simplest one. It's just a system with exactly one unit of deployment. Now, we talk about a monolithic application or monolithic architecture because it's a single application that covers the entire organization typically. So if I looked at a boundary small enough, like if I looked at a single microservice, you could say that one service is monolithic, but in a microservices architecture, I'm having multiple components together. So with a monolithic architecture, we're trying to strive to build one system to cover kind of every single case in the organization. And when I was looking back at going from monoliths to microservices, there were a lot of things I didn't like about the monolithic architectures. But there's clearly some value in those kinds of systems, and some systems people do build in this sort of architectural style. So what was wrong with some of these monoliths? Why do they not work well over time? Why was it so hard to develop with them over time? So I could see that there's a flavor of monoliths, which is the bad monolith, and these bad monoliths are ones who try to just jam too much junk into one single model, one single system, one single set of concepts. And I can especially see this on the data side, where we have multiple competing domains in the business, all fighting over the exact same data model. And we want to make a change to the business logic or the data. You're now having to go hunt down and figure out where all the different places that could potentially be affected by this one individual change. Now, of course, there's also just bad code as well. So you could say that, well, if the code has bad metrics, then it's also a bad code base as well, hard to work with. But I've seen the cleanest of code bases, the most well put together systems, well put together architectures, still where we're spending most of our time just trying to analyze, are we going to break anything? And it's really because the system itself doesn't have any boundaries around different areas of functionality. And those different areas of functionality, because there are no boundaries, will compete with another and actually becomes the business behind it, the business owners who compete with each other and will try to one-up each other to say, my feature's more important, and my feature's more important, because if they all are going to the same area that's affected, then one of them has to win. So what we're trying to avoid really is this big ball of mud that is trying to solve too many problems for too many different folks in the organization. And making a single change will have a ripple effect that we may not even know about until we actually go to production. But we don't want this, right? We don't want a bad monolith. We want a good monolith. And so a good monolith is just a monolith that is not bad. Or specifically, a monolith that is easy to change, one that's easy to understand, easy to modify, easy to extend. And the difference between a good monolith and a bad monolith is this ability to make changes over time and still add features over time and not worry about how many other things am I going to affect in the system. Now, we've tried different styles of organization over the years to try to make it easier to change the code over time. So when I first started doing development, we had this, which is the in-tier architecture. And the idea is that you separate each set of code by like its technical area of concern. So you have the UI layer that does all the UI logic, the database layer or the data layer has all the data logic. But even this became too difficult to understand and change over time. So you started to see different flavors of this over the years, different like shapes and circles and concentric things. But even then, I've seen systems that have, and I've been a part of them as well, in which we've developed these applications to the letter of the law of these different kinds of architectures. And still, at the end of the day, we noticed our ability to make changes over time go lower and lower and lower. So I found that no single application architectural style, especially ones where you're separating code by technical concern, don't actually result in a system that is easy to change further down the line. So the solution here is that we need to draw boundaries in our system. We need to carve off different areas of concern so that when I make a change to a system or make a change to one area of the code base, that boundary ensures that I am only affecting that one area and I'm not affecting every single other area. Now that's, of course, much, much easier said than done. So the rest of this talk is more about how we define those boundaries, how we move code around into different areas of concern, and then how do we enforce those boundaries over the lifetime of the application. Now, one thing that we saw that helped us get there is this idea of a vertical slice architecture. And the idea here is that whenever I'm adding changes or making changes to the system, adding code, I'm never just living in one of these individual layers. I'm always making changes across all the different layers of the application. But in these kinds of layered architectures, it's more difficult to understand if I make a change here, what other areas of the system does it affect? So the idea behind this architecture is that we build and organize our code around the axes of change, which stretch all the way from the front end all the way back down to the database. So instead of trying to just perfectly organize each individual layer to say all the UI stuff is here, instead I will build and organize my code around these different axes of change. And these then become those building blocks for larger modules. So when I say module, what does it actually mean? What are some of the characteristics of a module, and how does that differ from services? Well, the idea behind a module and a modular architecture is that modules must be independent and interchangeable, so they can live by themselves, and I can swap something out for something else without affecting the rest of the system. They should contain all logic and data to produce the desired functionality, and have a defined interface. So it has to have a public API. Now this seems awfully familiar to services for me. So when we talk a little bit later about migrating from modules to services, we'll find that a lot of the work is already going to be done for us because we've defined boundaries, we've defined contracts, defined interfaces. So what would it mean for a module to be independent? Now, no module is going to be completely independent, right? We're putting these different building blocks together into a single application in order to produce some functionality. And so if each module is completely independent, then I should just have separate applications altogether. But there's going to be some interactions between these. You can measure the independence of a given module by counting how many modules does it depend on, and then how many modules depend on it. So I'm looking at the afferent and efferent. I don't remember the differences between those two, but the arrow's pointing in and the arrow's pointing out. So a picture like this module, I would not say is independent because it depends and uses a lot of other modules for it to be able to produce its functionality. However, if we introduce some indirection and decoupling between different modules, then the number of arrows is reduced, and we also will reduce the number of direct dependencies between one module directly telling another module what to do. There are some cases when we have modules that are chatty, so they talk to each other quite a bit. They're just kind of going back and forth, calling each other's methods. And so for these two modules that have a strong dependency, that could be a good candidate for us to merge these two modules together. While those with a weak dependency with fewer arrows, they have more independence from each other. So in the cases where I have modules that are very chatty and very into each other's business, then that's a good case for us to just simply combine those two modules together. In order for us to understand what the different boundaries are in our system, it also is helpful to be able to have an architecture that makes it easy for us to move that functionality around. And so that's one of the reasons that we start with this idea of this sliced architecture, because if each individual slice is independent from each other, then the modularization of a system like this is simply grouping those different slices into individual modules. There's more to it, but this at least gives us a good head start in order to do so. But it can become challenging to understand, well, what should the different modules be? What should these boundaries of our system, how should we define the boundaries? How should we then pick and choose which modules should exist or which modules should not exist? So that's the other really hard part of these systems, is defining these boundaries and discovering them. Now with a microservice-based architecture, because a lot of folks I see are doing this sort of rewrite version of it, where they're rewriting an existing system into microservices, I often see that they spend a whole lot, just sometimes months, going through their organization and trying to define in the abstract what these boundaries are. What's nice about going from an existing system, going from monoliths to a modular monolith, is all the code is already there for what the system does. So it's up to us to understand how the system works and how it fits into the rest of the organization in order for us to then define those different boundaries. So yeah, the boundaries are easier to draw when there's an actual source of the information and the logic that we can look at, we can reason about, and we can understand. If we're talking about more in the abstract, like in this sort of rewrite scenario, then we're much more likely to get the boundaries incorrect because it's more of a theoretical boundary than the real boundary that exists in the system. We will get these wrong though, so plan accordingly, which again is easier if I'm working inside an existing code base than if I'm building a complete separate distributed system to the side where I won't know if my boundaries are wrong until much further down in the process. One possibility that I see folks use in order to define the boundaries in the system is to look at the organizational structure. So if the company has already kind of figured out how it should be organized internally, then perhaps that's a good way for us to organize the individual code base itself. Now, we can't ignore what's actually going on in the code, and we also don't necessarily want to just blindly trike and trust that the organization has, or the company has organized itself well, because I've been at plenty of organizations that every time there's a new CTO or CEO, there's another reorg, and everyone gets shuffled around. So we have to be a little bit careful about how much we couple our systems design to the organizational structure, just because that has a tendency to change and get completely upended over time. So maybe we do the opposite. Maybe we draw the boundaries of what we would like the organizational structure to be, and then hopefully, the organizational structure will follow based on how we build our software components and modules. Now, I actually have seen this work. I was dealing with a system in which we had separate sets of functionality kind of all scattered about. And then we realized that it was that different people were performing a very similar kind of activity all throughout the organization. And we realized, well, what's missing here is an organization, a piece of the organization who is responsible for, in this case, it was customer service. That there was no customer service department. It was just different random people all fulfilling this job. So we actually did wind up building our boundary around what we wanted it to be, which was around customer service. And then eventually, they actually just combined all those people together into one department. So it can happen, but it does require support kind of from the upper levels of the organization here. Another common structure I see is to align around value chains. So the idea here is that I take the overall business process of the organization, and oftentimes the organizational structure is defined as based on this, but I start to look at the different steps in the overall business process and then organize those boundaries around those different kind of macro steps in a business process. So like in an e-commerce application, you might have something like, well, there's a catalog because someone has to define what products you're going to sell. There's going to be a cart, the shopping cart, where people put items into the cart that they intend to purchase. There's going to be a checkout process. There's going to be a fulfillment process, a payment process, a shipping process. So these are kind of the macro steps in the overall value chain of the organization, and we'll often find that each of those different steps will have their own kind of rules associated with them, and oftentimes they have their own individual teams. So that's potentially a great example for us to use for organizing our modules, is just looking at what's the overall business process of the organization, and then organizing our code around those individual steps. Eventually, though, we'll run into data issues where no matter how much I modularize the code, if the data itself is still monolithic, I've never fully solved the problem of building out a modular architecture. Because those module boundaries do need to stretch all the way down to the database if we truly want independence between different modules. If any module can just kind of grab any other module's data, then that, again, is going to make it difficult for us to change that system over time, because every time I make a change to the schema, I have to worry about like who else is pulling in this information and for what reason and what purpose. So there's not an easy solution here, but a lot of times what I see is that there's like these central tables that cover all aspects of a business process, but only certain ones of those columns are used over time. So like these specific set of columns are written to during this part of the process, but then they're just read by other downstream steps, but never written back to. So you can kind of see that some parts of the business process own specific parts of the information, but other parts of the process will just be interested in that kind of read-only data. So finally, we looked at, could we look at different functional areas of the organization? So this is a little bit different than the organizational structure itself. We looked at, okay, are there different kinds of functional areas that the business has broken apart their different systems into? And sometimes these different functional areas have such different rules that we intentionally want to keep them very separate from each other. So we look at, if the business has already defined, like, okay, these are the different kind of functional areas of the organization, have they already decided that these should have separate rules, these should have separate processes, and perhaps just separate them out that way? So the last aspect of a module was around contracts, and that a module should have some kind of API that it enforces for its contracts. So a module without any contract or encapsulation will have the module that has its complete kind of vertical slice of functionality all the way from the database up to the top, but then other modules can kind of poke in and then get whatever data and whatever functionality they need. So I've seen cases like this where I've defined APIs that are only intended to be consumed within my single module, but another developer sees like, oh wait, I could really use that functionality as well. And since I'm just inside one single system and we're using dependency injection and things like that, it is ridiculously easy for us to just say, let's just go ahead and call that method over there that has this functionality, not understanding it was built for one specific purpose and goal in mind. And if that purpose or goal changes out from under me, that is the consumer of that, inside that set of functionality, and that's going to break me as well, and we're back to, again, the big ball of mud. So what we'd like to do is have explicit contracts and APIs that we intentionally expose between individual modules. And these APIs can be as simple as just an interface that is like, here's a bunch of methods, but this is something that we intentionally design to say, this is what I want to expose to the outside world as my capabilities. But everything else about how I fulfill those capabilities, that should be internal to my module and not be directly exposed to the outside world. Now, those contracts can take a variety of different looks. So it could be just synchronous APIs, where I just have an interface where I have one thing calling another. Or I could have asynchronous APIs as well, things like events, where a module publishes an event, and then sometime in the future, another module subscribes, and then consumes that event. So we can have both as part of our contracts that we expose. Now, in terms of how we do this, sometimes I've seen folks go to the extreme of actually building out NuGet packages or like public packages that other modules expose. But typically what I do is I just have in my project structure within the single monolithic application, I'll have explicit contracts projects that those are the things that I share between different modules, and no one can like directly reference the internal projects of each individual module. So that's all well and good, but like, how do we actually get there? How do we get to the point where our system is built by these different modules and we can pull them together into a single application? So again, my first step that I do is perform this refactoring to individual slices. So what I'm trying to do is take each individual kind of like activity or action or use case in the system and then take that step to kind of slice off that functionality and put it over to the side so that I can more easily reason about what things are related to each other. So we're taking the existing layers and breaking them apart and pushing them out, each of the different bits of code, into these individual slices and moving the code from those individual slices into a single place. On disk, like all the different files related to a specific slice of functionality will now be all co-located together on disk. Now what this allows me to do as someone who's trying to understand what parts of the system are related to each other, it becomes easy to understand like what's calling what if I don't have these kind of like these layer objects or these layer classes that go across the entire system. Because you look at the usages of something and realize like, oh, it's just used all over the place. But as soon as I start kind of pulling things out and putting them into these specific buckets, it makes it a lot easier to understand what different kind of individual use cases are dependent on the others. So these layer classes, I mean, this is really just as simple of, I take each individual method that is on these like kind of service class that could be used by anybody, and I move that into their own individual classes. And I put those individual classes in their own little feature folder on disk that clearly delineate and separate out that these things are separate from the others. Now, in terms of modeling these kinds of slices, the way I like to approach it is going back to the different kind of use cases in the system and noticing that for most of the systems that I work with, it's really just commands and queries are like the kind of building blocks of any kind of operation that I can perform here. And so any kind of like get into the system is a query with its own individual set of processing pipeline, and each post is a command then with its own individual processing pipeline. And ideally, these kinds of processing pipelines don't depend on each other, that there's no shared logic between these from the initial onsets. And then as we build up these different slices over time, when we start to see that these two things do have duplicate code, after the third time that we see that duplicate code, then employing that common logic into some kind of shared class. So a lot of times when I'm moving from these kind of very tangled systems, these tangled applications, into these individual slices, I'm defactoring a lot. So I am like reduplicating the code that may have been pulled into a shared location, but I want to prove that that shared code needs to exist after I've actually organized all the code into the different kind of slices of functionality. And then I can take that step back and say, okay, do these two sets of slices of functionality actually need to have this common logic that will change for the same reasons at the same time over the lifetime of the application, or at least for the foreseeable future? I also model these kind of slices to be very explicit about the inputs and outputs of the contracts. So I make sure that there's exactly one sort of request going in and one response coming out. And all of the logic needed to perform that action is that inside that one single class that performs whatever action is necessary to fulfill the functionality. So again, this can be a bit contentious on teams because like I'm removing a lot of structure that may exist there. I'm removing a lot of like potential layers and different, like someone has spent a lot of time like building out this sort of perfect layered architecture. But what I'm doing is trying to unwind a lot of those to get that sort of 10,000 kilometer, foot, meter view to understand like, okay, what is all the different pieces of functionality in the system, and now how do I then like group these different pieces of functionality to get together into these individual modules. But the idea here is that that I'm completely encapsulating each individual slice from each other. That I have a single request coming in, whatever is needed to do to perform the work is done by that one single class, and then I have one single response on the other side. Now, underneath the covers, we're still going to have some dependencies, even between these individual slices of functionality. That's just inevitable. So at some point, we probably have some kind of data model or domain model that these handlers are then actually interacting with. And those connections are going to be coupling between those individual slices. But in some cases, that's going to be OK. So if these sets of slices are doing similar sets of things in a common area with common data, then that is a good sign that perhaps that's a place we should define those module boundaries. Now, looking at an existing system to get to something like this, I first have to look at how do I model each one of these kind of individual components. So oftentimes, they're not built with this sort of architecture in mind, and so I have to see how do I refactor the existing code and to be able to get to these individual slices. So on the query side, it starts off by looking at, well, what are all the direct and indirect inputs into performing this query? So a lot of times I'm dealing with APIs, web APIs, or kind of a server application or server-side rendered HTML application. So for those, it's really going to be like the query string parameters. Those are going to be the inputs that say, here's here's the different inputs I need to be able to fulfill that individual query, as well as the URL route, right? So it's like this controller, this action, and these set of inputs define that individual interactivity. And that's oftentimes, too, how I even catalog my systems, is I just go through and look at all the available routes that correspond to different kind of actions the user can perform. And that tells me what are all the unique things that the user can do in the system, is just by looking at, OK, what are the API endpoints that exist in this application? And that tells me all the things that the user can do. The outputs can be a little bit more challenging. I'm basically looking at everything that is being pushed out to the screen or pushed out to the API. But sometimes these APIs they have too much data as part of them. They kind of overshare their data behind the scenes. And so I'll look at all the stuff that is directly passed through, but also what is actually being used in the consumer of these APIs. So in this case here, it's a HTML Razor page, whatever. So I just look at, well, here are the different items actually being shown on the screen. But if it's an API, I might have to go to the consumers of that API, the SPA, whatever, and say, OK, what fields are you actually using on this screen? Because I only want to share just the information that's necessary and nothing more. On the command side, it's a little bit opposite. So queries tend to have a big, wide output of the results of the query, where commands are typically the opposite, where I will look at the form fields on the page, and that becomes the different kind of the different properties on my command request object. So really, it's just looking at, OK, what information is being shown and editable on the form, and then that becomes my request object for the actual command. So if I'm building around these kind of task-based UIs, it means my slices of functionality relate fairly directly to operations the user wants to perform in the system. If I have a more CRUD-based UI where it's just edit and save and that's it, then I'm also often having to kind of reverse engineer, well, what tasks is the user actually trying to perform here with these different operations? But if I have a more task-oriented user interface, then it becomes kind of more, it's a bit easier to reason about the different sets of functionality in the system, because the UI itself is built around different areas of concern and different areas of functionality. So over time, I start to break out these individual slices of functionality into physically segregated code on disk, all the way from the front to the back. As I gather more and more together, I should start to see some patterns emerge that say, well, these sets of slices all are around this specific capability of invoicing, so perhaps that's a good candidate for building a module around those individual slices, because they're kind of all related to each other. This is a lot easier to understand when my code is already kind of separated out. So the very kind of first thing I have to do when I'm moving towards a modular architecture is to kind of break apart all these different tangled web of dependencies of the code itself. Now, these slices and the modules, they stretch all the way down to the database. And that is one of the more challenging aspects of any kind of separated out architecture style, whether it's microservices or modular monoliths, is, well, how do we deal with the database? Because Like today, it's just one single monolithic database, and I can just kind of query across the entire system at will, and not really worry about what boundaries may exist there. So there may not be any boundaries that actually exist in the database itself. So one of the challenges I run into is that I'll often have folks kind of treat their database as like the one single source of truth for the entire organization. And I've had these cases where like clearly there's contention between what different folks think is the single source of truth, but they'll have DBAs that say, no, if we can't agree about the source of truth of information in our system, how can we even be in business? Because we don't have a single source of truth for the data in our enterprise. So I've seen cases where like, we'll have a schema that's so normalized to the nth degree that it becomes really challenging to understand data changes over time. So we had a case where like, okay, a customer has an address, okay? And if that customer moves, should that affect historical orders? Probably not. But if I was like doing the actual normalization to the nth degree, then I have a customer, I have an address, and my order links to the customer that has their address. And so I've even had cases where DBAs were like, well, the way we solve this is to introduce temporal data. So I don't join just based on a key, I also join based on a timestamp. And then I go look at what point in time was this piece of data. And then it becomes like so challenging to understand what the data is over time. They always have to include this timestamp and understand the relevance of that timestamp. And there are even cases where the time can change. The time I want to join on depends on what kind of the operation I'm wanting to look at. So one good example we ran into was the organization had a catalog, and the catalog had catalog items, and each catalog item had a price. And to understand the total for an order, you'd have to go join back over to your catalog to get the catalog price. But of course, prices can change over time, so what we wound up doing was simply copying the data over from the catalog item over to the order line item. And then now that order line item has its own price. Well, there were a number of folks that were like kind of irate that we did this because like we're copying data. Now data is duplicated all over the place. What we found out was even though the data like looked to be duplicated, we found out that if I'm modeling my modules, especially around value streams or business processes, then that meaning can change over time. So we have an example like that I will see a price in an e-commerce system in many different places. And while that price value may look the same for a specific point of time, right? I put an item in my cart, or I look at the product on a page, I see it as a price, I click add to cart, and at that point, the price should be the same on both sides. I click place order, and then that price shouldn't change there as well. But again, if something happens to the price of the products after I place the order, should that affect historical orders? I hope not. Like that would be very confusing as a user to go back and say, oh wow, I got a better deal, but you already charged my card. That doesn't make any sense. So what we often find is that in this case, while the data may look duplicated at a given point in time, because each step in the process was separated in time, then we actually found that its meaning has changed as I've kind of pushed it from module to module to module. So at the very beginning on the catalog side, that is not the item price, that is the catalog item price. In the cart, it's not the catalog item price, it's the cart item price. And so on, it's the order price, order item price, and I don't think it actually changed during fulfillment. Let's just say we actually copy the price over there. So that's even though it looks to be the exact same data, its meaning has changed over time as that information has flowed through the overall business process and value stream of the organization. But there is hope. Like, it is possible for us to refactor our database so that we kind of break those dependencies down at the lower, kind of the lowest database level. It, of course, will require some buy-in. Because we want to make sure that we're not like upsetting people with these different prices or these different values flowing through the system. And we also want to make sure like we don't break a bunch of people's reports because like someone is definitely directly connected to our database somewhere with Excel or Power BI or whatever. And if we start making these changes, we'll start to know like who's who's the most angriest in the organization, because it's usually like the C something O that is Power BI directly to the production database here. But there is a way for us to perform this migration. And I'll have a link afterwards, but there's a great blog from the folks at Stripe that describe this exact process of migrating from one set of schema to another. And it basically starts out with, I have a single monolithic application that is just writing to the old value in the system. We make a single change that is now the monolith is going to be writing to the old location and whatever the new location is. So on its write paths, we will look for all the places where it's writing to the one place, and now we write to both places. Next, we find all the places that read from the old that should be reading from the new, but it also could be a case that some should read from the old and some should read from the new, but we're going to change all those read paths to then go point to the new location. And finally, we'll go back, once we've migrated all the data and migrated all the read paths, we can then go and remove that old write path, so now we're just writing to the new location, and then potentially we can even remove the old data if it's not in the right place. So in this manner, when I have those tables who have like 1,000 columns that is like the central part of the database, instead of me saying like, how do I share this data in like the single module that is that one wide table, what I'm looking at instead is, how do I carve out individual pieces of those really fat tables into those individual modules that should have ownership over those kind of slices of data and slices of information across the organization. Now, we still may need those like reporting views, and that's okay. Like, I may have a kind of a more broken down model in my transactional database, but we still may be pushing that data out into a data warehouse that then actually has like everything kind of jammed back together into a single table to make the Power BI users happy. Now, how do I know if I'm getting these boundaries correct? Well, first of all, we looked at the kind of coupling aspect of it. If I have two modules that are talking a lot to each other, then that's a good indication that I need to perhaps combine those two different modules together. But there are actual tools that I use when I'm building these kinds of architectures to assess and have a kind of a more objective metric to understand how different modules are related to each other. And these tools are collectively known as static analysis tools. I'm showing a screenshot here of Independ. This is actually showing a system that is kind of well factored to each other. But what we have here is, I'm basically looking at how different modules are coupled to each other. So I list all the modules on the left, and you can't see it, but it's on the top as well. All the modules are listed on the top as well. And then these numbers are the number of incoming and outgoing dependencies on each other. And there are different shapes and different kind of, you'll see different patterns of these boxes based on two modules needing to know each other very well. Now, unfortunately, I couldn't show like actual customer ones because they're all NDA'd, blah, blah, blah. So this one actually looks fairly well factored, but we will have cases where like, there'll be one module with like hundreds of dependencies and usages of another module, and that'll show up here as a really bright color. It says, actually, we see one down at the very bottom there. It's like 200 and something usages of one module to another. So there may be good reasons for that, but it's something that I use as an indicator to see, like, are these modules truly independent of each other, or should I then should I look at combining those two different modules together? Now, it's not a hard and fast rule here. So again, these kind of tools and these kind of pictures are just kind of indicators for me. They're not something that says, if you have this sort of measurement, then you must go ahead and combine these things together or split them apart. I'm kind of just using it as another data point to tell us how well are we doing in building out and separating out these individual modules. Now, functionally, these are broken out into individual assemblies, so it makes this kind of analysis easier. But I'm also looking at all the other kind of software metrics as part of doing this to say, like, how good is the code inside of this one single module? These kind of tools will tell me that as well. But this dependency matrix will tell me how each module depends on the others. Now, if we're doing a okay job at this of breaking down modules or breaking down our monolith into individual modules, we may get to the point where we say, like, these module boundaries we feel pretty good about them. We've been able to isolate each module from each other, and we've been able to achieve that, hopefully, that developer velocity that we intended to with this kind of architecture. So that may be the case that we'd want to look at extracting these modules into individual, like, parentheses, microservices. And for me, this gives the greatest chance of success for a microservice-based architecture, because if I've already proved out my boundaries in a system that makes it easy for us to kind of move boundaries around and understand, like, well, at least easier than a microservice one, then that gives us kind of the greatest hope for success for building out a microservice-based architecture. If I'm just kind of guessing or having more theoretical sort of drawing of boundaries, then it's going to be much more challenging for me to get those boundaries right. With an existing monolith, though, like, the code's all there, the features are all there. It's just us, like, rearranging and enforcing those boundaries to make sure that modules have independence from each other. But we're working off existing code, not just kind of theoretical maybe code. So the reason why I also find there's a nice symmetry between a modular architecture and a microservice architecture is because microservices are trying to achieve a lot of the same goals as modules. So microservice is supposed to be independently deployable. So that's different than a monolith, right? Because a monolith, the modules are all deployed together into that one single monolithic deployment. But in a microservice architecture, they're independently deployable. Now, what this can give us a lot of benefits, right? If we have specific scaling needs with one of our modules, and that's a good candidate for us to say, it's expensive for us to scale the entire monolith up, but if I could just pluck this one module out over here and put it over there, then I can scale or even design that module with more independence than the rest of the system. Microservices are also supposed to be loosely coupled, just like modules are supposed to be loosely coupled with each other. But the last one that makes it really different is that it's autonomous. And autonomy is just, well, it's a collection of attributes to say that a service is autonomous. But that is a higher level of independence than a module would have. A module has to live within a single runtime, so we can't say, like, well, this microservice or this module is going to use Go, and this module is going to use Rust, and this module is going to use C#. If they're all living together inside of a single application, we're much more constrained in our technology choices. But microservices, because they are independently deployable, it also kind of opens the door of any kind of, it opens the door to technology choices that we would not have had with individual modules. So yeah, autonomy, what is this? So services have to have independent ownership, availability, and delivery. So again, this is quite different than a monolithic architecture in which I have, like, there's no independence of availability and delivery. It's like they all get delivered all together. They manage information and access to that information. That is the same as modules. They handle failures so that it does not bring down the entire system. In a modular monolith, we do have to worry about failures of individual modules, but typically you assume that, like, the module has to work in order for the entire system to work. It's not like I can have one module kind of go down and expect to have the system. It's either the entire monolith is up and running or it's not up and running. There is no kind of middle ground here. And finally, it maintains those contracts. So it understands, it maintains the contracts, the APIs that it wants to expose to the outside world. Again, very similar to modules here. Modules also define their own public contracts, but those public contracts are not consumed by other systems and other applications. Those contracts are only consumed by that one single application. So that also means that the choices of what those contracts represent and the technologies used to expose those contracts are quite different from a monolithic architecture versus a microservice-based architecture. In a modular architecture, I'm probably not exposing, like, web APIs as my API between all my different modules. Typically what I have is just an interface that has a bunch of methods, and then that is the contract I expose to the outside world, as well as, like, any kind of messages or events, commands, that sort of thing that goes onto a bus. So we start out with something like this, where I have ideally two relatively independent modules that communicates via well-defined contracts, but those contracts are all in process and can even be not even on disk. So even here where I have a publish of an event, that may not actually make it onto a broker or a bus or a queue. It could just be an in-memory publishing of an event that is immediately then consumed by the other module. But as I move towards services, what we'll do is start to break apart these kind of in-process calls into now distributed calls, where one system will no longer just directly call the code behind an API, and that's still behind an interface, but instead we'll start to go through some more formalized APIs, either through web or messaging or some combination thereof. So because, though, I already have this contract of our module, it actually makes it as a great place for us to convert that individual module's contract into now a facade. So instead of that facade or the implementation of that interface directly interacting with the module's code, instead what we'll have is the facade living in the monolith. Now instead of talking directly to the module's code, can instead now talk through an API. Similarly, when we're talking about those event contracts, those events will start typically using synchronous-based in-memory, in-process messaging, and are now going to a more out-of-process async sort of messaging. Now, we do have to make sure, though, in this kind of transition, where I go from a sync to an async world, I have to be very, very careful that there's not an expectation from the user side that the consumption of that event happens immediately. So if it's now happening sometime in the future, then what I don't want to have happen is that user goes to a screen, clicks a button, goes to the next screen, but that event has not been processed yet, and so they don't see the expected side effects of whatever the operation they were performing. So in those cases, when I'm moving away from a synchronous to an asynchronous sort of world, I'm always asking myself, within a given set of code, what is the primary activity of this, whatever action the user is performing, and what are the other side effects that are not the primary action the user was taking? What are the things that need to happen now, and what are the things that can happen later? And if those things can happen later, and those are potentially a great choice for me to use async messaging instead of a synchronous in-process messaging. But I have seen cases where people just basically blindly replace all of their sync messaging with async messaging, and then the users are complaining why the system is broken, or at least doesn't make sense sometimes because they didn't realize that behind the scenes there's a queue that has put their work to the side, and then sometime in the future it actually then consumes that and picks it up there. So yeah, don't just blindly replace async with sync or vice versa without having heavy consideration for the user experience here. So, to wrap things up, no one ever wanted the big ball of mud. We never set out in our monolithic architectures to have it get worse and worse over time. It was not something really everyone ever intends to do. I do a lot of these kinds of assessments of code bases to figure out kind of how they got there and what direction they should go forward. And at no point have I encountered a big ball of mud where we had architects and developers yep, that's what we set out to do. We meant to do this. But the challenge is even the most kind of layered of architectures will not save us from those big balls of mud. We need to build our system around slices of functionality and modules that go all the way from the front all the way to the back. So the user interface all the way to the database. Second one, the boundaries are actually enforced boundaries, not just theoretical ones, are critical for us to facilitate change over the lifetime of our system. If we don't have any boundaries in our system, then anyone can kind of call any code, anyone can use any data, and that kind of coupling is what leads to the big ball of mud. That it's not just one method is too long or whatever, it is more that if I try to make a change to the system, I can't reason about all the other downstream effects. And it's only by building these boundaries around sets of code in our systems that we can reduce the number of side effects for any kind of change. Third is that slices make it much easier for us to move towards modules because we're already carving out the sets of functionality in your system into these like very thin sort of slices that go all the way from the front to the back. Once we've achieved that to some sort of degree, I can now take that step back and say, okay, how can I organize these slices together around modules and then now build these enforceable contracts to not let kind of anyone do anything to our data and to our code. And finally, this is something that I've definitely seen over the years, is that shaping boundaries is much easier when I'm inside a single code base. It's much more difficult if I'm separated out with different teams, doing different services at different parts, the organization. It's much easier to say, let's start with an existing system and an existing application, because we already know that it does what it's supposed to do, well, I guess allegedly, and the code is already there, so it doesn't lie about what purpose it serves. It's all there in the code. So if you want more information about this, I'll be sharing some links on my Twitter later. There aren't a ton of books about this right now. There's a lot of microservice books, so I think we're seeing the people kind of catch up to be able to writing these sort of books. But I do find that a lot of the literature around microservice-based architecture that talks about contracts and boundaries and ownership, those same kind of techniques are applicable to a monolithic architecture. It's just that everything's now deployed as a single unit as opposed to deployed independently. So thank you very much. I'll be hanging out afterwards for questions. Otherwise, I hope you all have a great rest of the conference. Thank you.